Hello, 8 Purple. We're going to pick up right where we left off yesterday. Yesterday, the purpose of that class was to explore some data um, that told you something about how the moon's elevation changes throughout the year. And so, just to recap what we kind of came across yesterday was that if you are tilted towards the sun in the summertime, if the northern hemisphere is tilted towards the sun, that makes the sun appear nice and high. The sun takes a very high path across our sky. But due to the geometry of moon phases, that means that we'll be tilted away from a full moon. And so the full moon must take a low path across the sky. Now, conversely, 6 months later, in the wintertime, when our northern hemisphere is tilted away from the sun, we are tilted towards a full moon, which means that the sun is taking a low path across the sky, and the moon is taking a very high path across the sky. And that concept can be changed for whatever phase you want to talk about. So if we wanted to change these two new moons and put them in these positions, then that pattern might be flipped. So in the summertime, we're tilted towards the sun and a new moon, so they're both going to appear high. And in the winter, it's the opposite. And you can see similar things that would happen if you put them into a first quarter moon or even a third quarter moon. So these different phases have different elevation patterns that are associated with them. So that's what you were supposed to graph yesterday, and hopefully this is something what your graph came out looking like. So if we look at one of these lines, that should represent what that specific phase, this blue line is the new moon. So what the new moon does throughout the course of a single year. Um, and we can see that it's low in wintertime and very high in the summertime, and then it comes back down to being low as it approaches winter. The opposite of that is the full moon. So we just went over that. That's high in the summer. I'm sorry, the full moon is yeah, high in the wintertime, low in the summer, and high again as it comes back to winter. And then you have your first quarter and third quarters, which are kind of offset by 6 months as well. So some really interesting patterns that come out of it. This should look kind of reminiscent of something. When you were filling it out, you may have seen that there's kind of like a double helix aspect going on. And that shape is actually a common theme throughout the whole year. We haven't much talked about it, but it's actually got a name, and it's called a sine wave. A sine wave is a graphical representation of a smooth repetitive motion. And so you may have seen it when you had this solar terminator exercise that we were doing. It's definitely present if you were to examine the electric and magnetic fields and the forces that correspond with them. And like I said, with the double helix, while that's not exactly a true uh, example of a sine wave, there are some commonalities there, and it's kind of neat in the whole thematic uh, reproduction, the repetitive kind of concept that happens with DNA. So just so you know, a wave consists of these following parts. This is the anatomy of a wave. This is the crest. This is the trough. The amplitude is how high is the distance from the crest to the midpoint. The wavelength is the distance from one crest to another. And then here, I want to bring your attention to these parts. When it crosses this midpoint, there's this intersection here, that's called a node. And that's going to be important, not so much today, but in a couple of classes, maybe tomorrow and Friday. Um, that will be something important. All right, so I don't know if you're going to pick up on this. Probably not. This is kind of an animated GIF that I threw together, but because my computer is recording this in 8 frames per second and this animation is pretty choppy to begin with, it may not get you the right visual. It might not be spot on, but that's okay. We're mostly going to be paying attention to what's up here anyway. So this is the stitching together of all of the graphs from the spreadsheet yesterday. Here's January, February, March, April, May throughout the year. The red line represents what the sun is doing in its altitude, and the blue line represents the moon's changing altitude. And you can see that the moon is changing its altitude so much more frequently than the sun is, right? We've got this one concept, this one drawn out line for the sun, and so many ups and downs, and that's the main difference between those two elevation patterns. One thing I want to point out is that if you look at this graph, it's really a position time graph. So you could do some serious analysis in terms of position divided by time and look at the acceleration of these objects because these are all nonlinear graphs. They show um, some examples of what's the word I'm looking for? Acceleration. And the reason they're accelerating is because they're going in circles, right? And they're doing that revolution. It's also reminiscent of how the way that water moves in a in a wave as an energy wave passes through it. So you might think that water moves with the wave, but in reality, if you were to follow this one red dot, like that one water molecule, the water molecules tend to stay fairly stationary. They might make this little circle every now and then, or kind of do a series of circles, but for the most part, the molecules themselves aren't moving. It's the wave energy that's moving through the wave. If you think of the red circle as one of the moon phases, you can see how it's got this kind of up and down aspect to it, and it's kind of reminiscent to how that occurs. Okay, so the big picture here is that the elevation of both the sun and the moon are determined by how much a hemisphere is tilted towards that object. And because the moon goes around us every 29 and a half days or so, we have a lot more frequent uh, elevation changes when compared to the elevation change of the sun, because it takes 365 days for the Earth to get around the sun. And because of that, we have some really interesting patterns that result when you compare the altitude of each phase during different seasons. So, for example, the sun we know is low in the winter, it gets higher in spring, it's the highest in the summertime, and then it starts decreasing in altitude in the fall. The new moon does the same thing, it follows the pattern of the sun. The full moon is the opposite of that. The first quarter has its own pattern associated with that, and then the opposite of the first quarter would be the third quarter. So anyway, that's it. We're done with moon phases. As far as the patterns that are associated with them are concerned, we'll be starting up eclipses pretty soon. There's an exit ticket today. Make sure you fill out those questions, and have a good day. Have a good day. Thank you.